Hello everyone. Welcome to this presentation about simplifying the TPC benchmark C, where we're going to focus on testing and development as opposed to competitive marketing. I am hoping you're here to learn a little bit about the TPC benchmark itself, how you can run your own tests based on this specification, and I'll go over what you can get out of the results. This is not a trivial benchmark to run, so if competitive benchmarking isn't something you do on a regular basis, you're probably looking for an easier way to run something like this. But I won't go over how you're going to produce your own TPCC publications because that's quite an endeavor in itself, in addition to being able to run this workload. So the point is that we're trying to learn how our system is performing, including the hardware and software, or to evaluate something that you're thinking about using. I will quickly introduce myself. My name is Mark Wong. I work at EDB as a performance engineer. In a previous life, I've got to work on a couple of TPC publications and have helped develop a handful of open source TPC kits. With respect to the Postgres community, I am a major contributor. I'm also on the community's funds group. I've helped mentor in the Google Summer of Code project. I also help organize the Portland Postgres users group, and I am currently serving on the board of directors in the United States Postgres Association. So what is the TPC Benchmark C? It is a publication by the Transaction Processing Performance Council, more commonly referred to as the TPC, a nonprofit corporation composed of hardware and software vendors. The TPC Benchmark C is also known as the TPCC, or the C for short, as is one of many benchmark specifications published by the TPC. So I'll just be focusing on the C for this presentation. And the C is an OLTP workload representing a wholesale supplier that covers various sales districts with a number of geographically distributed warehouses. So there are 5 database transactions modeling people who are sitting at terminals typing in orders. For the more database-oriented folks, this database is designed with 9 tables of varying sizes, attributes, and relationships with non-uniform distribution of data access through primary and secondary keys. So people running this benchmark are producing publications that tell you about system performance, pricing, that incorporates software, hardware, and support costs. Here is a diagram showing the type of application that the C is modeling. It is a traditional 3-tier client-server model. On the right, there is a database management system, which may be distributed. In the middle, there are clients using C terminology, meaning that it is a transaction manager. And on the left, there are a number of emulated terminals that are connecting to the database through this client, this transaction manager. So people are typing in orders, that data is sent to the client, and the client is executing database transactions. And we do mean transactions in the traditional database sense. The C specification explains how everything needs to be implemented and executed. There are a number of things to be aware of, but what I want to focus on are the things that are required to produce an official publication to show how much work, time, and planning is actually involved in running a benchmark, running this specific benchmark. So this is a 100% do-it-yourself benchmark. There is no code supplied by the TPC to help you execute this. So what this means is that you have to write your own data generator, you have to write your own transaction logic, implement your own database transactions. You have to write the code for your transaction manager. And you have to write the code to emulate the user at the terminal that is driving this benchmark. On top of that, with all these different components, you're probably writing your own test harness, so that's easier to start all the individual components, all the clients, all the emulated terminals, and then post-process all of the data so that you know what your transaction rate is. Furthermore, auditing is a required aspect of doing a publication, and you have to develop your own code to help the auditor show that you executed the benchmark correctly. Then, these TPC benchmark publications require that everything that you are benchmarking to be commercially available as well as commercially supported. The TPC-C is a benchmark that needs to be run for a minimum duration of 8 hours to satisfy the durability requirements of the benchmark. One of the more complicated aspects of this benchmark is understanding that the results are directly tied to the scale factor. In other words, the size of the database, where the scale factor is equivalent to how many warehouses have been built. The number of warehouses also dictate how many users are emulated. So for every warehouse that is built, you're supposed to emulate exactly 10 users. And with each of these users, you're supposed to emulate its keying and thinking time, where the keying time is supposed to simulate the amount of time it takes for a person to enter information into a terminal. And the thinking time is supposed to simulate the time it takes to determine what transaction to run next. In other words, whether the user is entering a new order or reviewing stock. So given all those considerations, what this means is that there is a theoretical limit of being able to produce 12.86 transactions per minute per warehouse of this database. A couple of practical examples. If you have a 100 warehouse database, but get nowhere near 12 transactions per minute, then there's a severe bottleneck somewhere in the system that is preventing you from executing from getting the throughput that you're supposed to get. Similarly, if you see that you are producing 12 transactions per minute and that the system is severely underutilized, then in order to produce more transactions, you're supposed to increase the size of the database. Now, can we find a more reasonably priced system? Let's interpolate some of this data for a 128 core system. I semi-arbitrarily picked 128 cores just because it rounded off some of the numbers. So with 128 cores, we should be able to expect to get 1 million transactions per minute. But we still need to emulate over 700 million terminals, and we still need at least 40 cores to support the number of transaction managers we need to get that result. And then if we look at the cost, that's still over $2 million. I thought it would be fun to give some perspective on hardware costs. In 2020, the top published result produced over 700 million transactions per minute. To get this number, you need to build a database with over 50 million warehouses. For every 10,000 warehouses, you need to generate about 1 terabyte of raw data. So this means that over 5,000 terabytes of data was generated. Also, this means that over 500 million terminals were emulated. To support this result, over 65,000 processors were used for the database system. Then over 20,000 processors were used for the transaction manager systems. And we don't know how many additional systems were needed to emulate the terminals. Regarding storage, we need to hold the 5,000 terabytes of data and have enough storage for whatever the resulting indexes and expected growth is for the logs and tables. And we don't know how many 8-hour tests were run on the system. So when we factor in the hardware costs, which needs to include the database systems and just the clients, the transaction managers, this totals almost 2 billion US dollars, which also includes the support for the hardware and software. So we need to start making things simpler just to make it easier to run this kind of workload and to cut down on costs. First thing we can do is start ignoring any publication requirements. So we won't worry about whether the hardware is currently supported. Maybe you're testing on hardware you already have. Maybe you want to test on something new. I do suspect folks here are more likely to test a commercially supported version of Postgres, but probably not interested in testing a commercially supported transaction manager. And I do think it's useful and possible that some people will want to be testing versions of Postgres that are in development, maybe testing a bug fix, testing a new feature. So with the type of testing I suspect people here are most interested in doing, I suspect that getting an independent third-party auditor to make sure you're running the benchmark correctly is probably not necessary. And this cuts down on the amount of work for you as the benchmarker to provide the things that the auditor needs, such as verifying the ACID properties or showing that you can survive a power failure. Except for those of you planning on doing testing on bare metal, I'm not sure if there's an application or program that can help you acquire bare metal systems. But for the growing age of the cloud, containerization, virtualization, there are tools that can help you provision resources in those kind of environments. While I suspect not everyone here is going to be provisioning hundreds of systems, I suspect it still might be nice to be able to use the utility to even set up a handful of systems. Now, EDB provides an open source tool for provisioning resources in the cloud, and I admit that this area is a little bit outside my area expertise. So if there are folks in the channel chat watching this recording, it might be nice for people to shout out anything else people should look into to help them provision resources like this. But having a tool that can provision resources to could make things easier, such that you can define the database system that you want to use, the size of the storage, the number of processors, the memory, as well as the systems you need for the client transaction manager tiers. And then be able to set up other components you want to see get stressed under this kind of workload. For example, how many standbys you want to see in the system, whether or not there's a backup server that's also managing your backups while under load, any other systems you might use to test, say, high availability, what happens if there's failover. Once you have the infrastructure in place, whether it is bare metal or virtual systems, they still need to be set up. EDB provides a set of open source Ansible playbooks that is also available in the Ansible Galaxy that can be used to install Postgres and other benchmarking tools. So right now we have some playbooks that support HammerDB and DB2. I'll go into those a little bit more later. And these playbooks will handle tasks such as installing Postgres, doing some initial auto-tuning of Postgres, set up the authentication to allow connections from the clients and driver systems that you have set up, Install these benchmarking tools, create users, set up SSH keys, set up SSH with what hosts it should know about. In the current age of open source and freely available software, you don't even need to write your own benchmarking kit anymore. There are numerous options out there. They do vary a little bit in how compliant they are to the benchmark specification, but these are probably minor details at this point. Now, I should say that I am the primary author of this one particular kit called DBT2, so be prepared for a little bit of bias and lack of knowledge of some of these other kits. And while I believe DBT2 is the most comprehensive kit out there, it doesn't mean the other one shouldn't be used, but I will use it as a point of reference so you can see what is capable, what are the possibilities of what you can do with any of these available kits. I'll just take a couple moments to mention a few more details about each of these kits. DBT2 contains C applications with a pile of shell scripts to help run the test. HammerDB is written in Tcl and is an official project of the TPC. Benchmark, SQL, Benchbase, and OLTP Bench are all Java applications. And all of these support multiple databases, including Postgres. Some support SQLite, MySQL, MariaDB, Oracle, SQL Server, DB2, CockroachDB, and others. I will actually take a few more moments to talk more about the performance of some of these test kits, and some of my bias will bleed out here. First, quickly want to thank Equinix Metal for providing hardware to the Postgres community, which allowed me to run some of these tests. I do believe that the performance and efficiency of these test kits can be an important factor of how you choose which one to use. Now, you still have to ultimately decide for yourself between which one of these is more comfortable for you to work with versus how quickly you'll be able to run a test for the size of the database that you want to test. One aspect I looked at was the performance of the data generation. In order to generate 1,000 warehouses, we need to produce about 100 gigabytes of data. So I took a look at how DBT2 did versus HammerDB to generate 100 gigabytes of data with one stream, just to establish a baseline. So DBT2 took about 35 minutes on this system, and HammerDB took about 270 minutes. And we can extrapolate how quickly we can improve those times based on the degree of parallelism we have. Based on the number of processors we have, we can carve up the data file generation and save a significant amount of time by producing smaller ones. Now, Benchmark SQL and Benchbase couldn't just generate data files, so I went ahead and tested how quickly it could take to generate a 1,000 warehouse database, letting each of these kits utilize as much of the processors, utilize as many of the processors that they were going to use. So there were 22 cores available on this system. DBT2 generated a database in about 27 minutes. Benchmark SQL took about 40. Benchbase took about 148 minutes. And this included the loading of the data as well as building indexes and doing whatever vacuum and statistics analyzing that they were going to do. So then, depending on how large of a database you want to test, you may want to take a closer look at what some of these numbers could mean for you. The last consideration in simplifying this benchmark is thinking about how we're going to execute it. How we're going to execute it can simplify the resources we need in order to execute it, the number of systems, for example. The first common thing folks do to simplify things is to emulate the users, the terminals, to not incorporate any thinking or keying time. Have them execute transactions as fast as possible. The overall effect this has essentially allows us to drive up the system load without having to increase the database size, increase the number of transaction managers, or increase the number of terminals that we're trying to emulate. The second common thing that folks do is not to have a terminal work within a single warehouse. The specification, a user is supposed to only work in whatever terminal, whatever warehouse they're assigned to for that terminal. So meaning that each terminal can randomly change which warehouse that they're working in. In some ways, this kind of compensates for not simulating keying and thinking time. So a terminal will execute a transaction against one warehouse, and instead of executing the transaction in the same warehouse, it'll pretend to connect to a different warehouse to continue working in that space. Then with all these simplifications to emulating a user, emulating terminals, another thing that a lot of these kits do is to simply do away with that third terminal tier altogether. That to move all of the logic of emulating a user directly into the client. And despite all of these simplifications, there are still many ways to execute this benchmark. Many ways that this test can be used to test the system or evaluate the hardware and software. So one thing that EDB has done is to create another open repository, open source repository called EDB Benchmarks, which is just a set of examples of how to execute, well, DBT2 in particular, but it's only just started and is not intended to be limited to one particular test kit. So a couple of examples that we have in there now is to use test kit to determine, to characterize what the system behavior is when you increase the number of database connections. The other example we have is how to execute this in a 2-tier versus 3-tier client server configuration, just so you can get away from using some of the extra systems that you may not necessarily need to drive the system effectively. If you made it this far, it means you have some test results that you need to look over. There is a dbt-reports repository on GitHub that folks can go to view these reports through a browser online. There is a fair amount of data that the dbt2 kit collects that I want to use as an example of what all these kits should be able to collect and report on. But for this presentation, I'm going to show various screenshots because I think that might be a little bit easier to talk through rather than to scroll around a huge amount of data. So this first set of data that is captured, that I'm showing here, is what the most typical metrics that people want to look for in a TPCC-like result. What you'll see are the 5 transactions that are executed, the percentage each one was executed, what the average response time was on the 90th percentile response time, how many times each one was executed successfully, how many times they were rolled back, then how many new order transactions were executed per minute, how long test duration is, and so on. For the purposes of understanding whether or not that the workload was executing correctly and within the performance that you should be expecting, the average response times and the 90th percentile are a couple of the indicators that help tell you whether or not the test was performing efficiently. Along the same lines, the rollbacks and the percentage of transactions that are aborted is another indicator that the test was executing correctly. Another way that we can look at the test data to determine whether the test was executing efficiently is to visualize the response data. So what I'm showing here for to primarily focus on the delivery transaction are two charts. One is the aggregated transaction per minute over time on the left, and on the right is a scatter plot of the response time of each transaction when it was executed. So some of the things that you want to look at here is if this workload is executing efficiently, you want to see some fairly even trends. So you want to see that the aggregated transaction per minute over time is relatively flat. Similarly, with the scatter plot of the response times, you want to see that most of the response times are fairly consistent throughout the test. A couple of the things that we might notice when the system is not performing efficiently, you'll see spikes of response times or spikes and changes in what the aggregated transactions per minute is over time. Could mean a number of things. A couple common ones could be that the auto vacuum process in Postgres might be going off more than you think. It could mean that checkpointing is going off more often. Well, not just more often than what you think, but maybe not tuned so it isn't overtaking the system. And it's not just about the database. Sometimes it can imply things about the operating system that is not tuned. For example, how often the buffer cache is flushing, or whether you have something like transparent huge pages on Linux taking over the system. If you're testing Postgres and your test kit is collecting data from Postgres, a couple of things that could be good to have are the parameters that are set in the database, as well as capturing query plans, just in case you are concerned about whether you have the right indexes in the system. Then if you're capturing all of the database statistics out of Postgres, you'll be able to review the database level statistics, such as the block hit ratio, as well as commit rollback rates. If you're capturing the table statistics, you can start reviewing similar things like the various hit rates on each of the tables. And again, capturing all the statistics on the indexes will also tell you what the various hit rates are on the indexes, as well as give you an opportunity to determine whether some of those indexes are being used or not. Some of these kits will hopefully also help you capture system statistics, so you can review the processor, memory, I/O, and network utilization from each of the nodes. One thing that could be nice for the developers is also to take samples of to take profiles of the system, so you can review various call graphs and even flame graphs. Towards the bottom of this page, there's also a report on collecting per process statistics on each of the system. And this particular test, it's what we're calling the driver here on the system named Potassium, is the DBT2 process that is simulating both the driver and the client at the same time. So there's only one of these processes listed. But clicking on that link will pull up data that is collected for that particular process, so you can review what the processor, I/O, network utilization, memory utilization, and so forth is of that particular process. Reviewing details like this help you know whether your driver client systems are sized appropriately in order to drive your database hard enough. Then finally at the bottom of the page, there is a section of per process statistics on the database system, or for Postgres in particular. These will be charts showing processor, memory, disk utilization, the the various all the various system statistics for the processes, such as for the processes that get started from auto vacuum, the background writing, checkpointing, logging, replication, the stats collection, and the transaction writer, the wall writer. And this wraps up my presentation on the TPC benchmark, how to simplify it and understand the results. Thanks everyone for listening.